In this video, we're going to look at how to come up with the potential rational zeros of a polynomial function. We're also going to look at testing those potential rational zeros to see which of them actually work in the equation. Up here at the top, I have what we're going to do, the theorem here on rational zeros of a polynomial. It might be easier just to look at this here, this fraction. Our possible rational zeros, we're going to look at the factors of the constant term a sub 0, and we're going to put that over the factors of the leading coefficient a sub n. Okay, kind of confusing. Let's just kind of jump in here and take a look. And I'm sure I'm going to need more room than this, so let me move this down. Okay, so I'm going to start, and I'm going to look at the factors of the constant term. The constant is the number that does not contain a variable, the term that does not contain a variable. So the factors of -8 are, well, I can multiply -1 with a +8, and that will give me -8. Or I could multiply a +1 with a -8. Or I could do a +4 and a -2. Or a -4 and a +2. So I would say the factors of -8 are, there are 2, 4, 6, 8 of them. But instead of writing them in this long list here, we can be a little more concise and use the plus or minus symbol. So I'm going to say that the factors of -8 are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Now, the other thing that helps us to determine the potential rational zeros of a polynomial function would be the factors of the leading coefficient, which in this case is +3. To get +3, we could multiply 1 and 3 together, but we could also multiply -1 and -3 together. Just as I did before, to write it a little more concisely, I'm going to write plus or minus 1, plus or minus 3. So the potential rational zeros of the function would be the factors of -8 over the factors of 3. And by the way, a rational number can be written as the ratio of two integers. So basically we're looking at fractions, or whole numbers are actually, and integers are rational numbers as well. We could write those over 1. So we're coming up with what are the potential fractional answers of the equation here. Imagine you were trying to solve 0 equals 3x to the 4th plus 14x cubed, so on and so forth. So we're looking at solutions to that equation that are also rational. Okay, now I'm sure your instructor is going to want you to simplify this further. We want to put each of these factors over plus or minus 1, and also put each of these factors over plus or minus 3. So putting each of those over plus or minus 1, we're just going to get the same thing here. And then we're also going to put each of these over 3. So plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, and plus or minus 8/3. So all of these are potential rational, whoa, got a little crazy there, potential rational solutions, there we go, to that equation. So imagine solving the equation f of x equals 0. These are our potential rational solutions. So this theorem helps us define the potential rational solutions. We're not sure, though, what the potential irrational solutions might be. We are going to see some irrational solutions in the last example. So we'll discuss later how we would work with that. Okay, let's do another one like this. Move this down a little bit here. So we want to come up with the potential rational solutions of this equation. We're not actually going to check them yet. That's going to be on the next page here. We're going to check the solutions, but for now we're just listing the potential ones. So we start with factors of the number term or constant. Factors of 12 would be, I'm going to go ahead and just start with plus or minus. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. This is because 1 times 12 equals 12, 2 times 6 equals 12, and 3 times 4 equals 12. So all of those are factors of 12. Our leading coefficient is a 3 again. So the factors of 3 are plus or minus 1, plus or minus 3. To get a full list of potential rational zeros, we're going to put the factors of the constant in the numerator. Then the factors of the leading coefficient go in the denominator. And we'll go ahead and simplify this. So we're going to put each of these over 1. That's just going to give us the same list as the numerator. But we're also going to put each of those over 3. So plus or minus 1/3, plus or minus 2/3, plus or minus 3/3, plus or minus 4/3, plus or minus 6/3, and plus or minus 12/3. Now, before I say this is my final answer, I don't want to be redundant. I don't want to include the same solution or the same potential rational zero twice. So I look and I notice that I have 3 over 3. But 3 over 3 is the same thing as 1. So I don't want to list this as a separate possible rational zero, or rational zeros. There'd be 2 with plus or minus. So 3 over 3 is 1, so I don't need this. 6 over 3 is 2, so I don't need that. And 12 over 3 is 4, so I don't need that. So, we don't want to list a potential rational zero more than one time. So if your fraction simplifies into something that you already have on your list, go ahead and cross it out. So these would be our potential rational zeros of this polynomial function. Now, on the next page, we're actually going to find them, not just list the possible ones. Before we apply the theorem again, I do want to show you one like number 3 that can be factored by grouping. If it can be factored by grouping, then you don't have to worry about this theorem. So something like number 3 we've seen before. We saw it earlier in the semester. We can factor by grouping. And when factoring by grouping, we have the factors x squared minus 9 and x minus 2. But x squared minus 9 is a difference of squares, and I can factor it further. And so if the product of these 3 factors equals 0, then that means that x plus 3 equals 0, or x minus 3 equals 0, or x minus 2 equals 0. So we get 3 solutions. Those 3 solutions are -3, 3, and 2. If you want to write x equals, you can. So x equals -3, 3, and 2. All right, so we did something like that earlier in the semester. We did not need to apply this theorem in order to solve that equation. Okay, but now let's look at something like number 4. Number 4 does not factor by grouping. In fact, let me try it. Let me show you why it doesn't factor by grouping. If I try to factor by grouping, I don't have the same binomial in the parentheses. Okay, here I have x plus 7, here I have x minus 3. Okay, not the same thing. So this equation needs to be solved in a different way. We cannot solve by factoring. So what we do is we list the potential rational zeros and then we test them into the equation. So we've got factors of negative 12, and factors of negative 12 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Then we look at the factors of 1, the leading coefficient. All right, so factors of 1 would just be plus or minus 1. So our possible or potential rational zeros would be all of these over plus or minus 1. But we know when we put all of those numbers over 1, we just get the same thing. So here are our possibilities. Now to figure out which of them actually work, we just plug them in. And we're looking for an outcome of 0 when we plug in these possible zeros or solutions. Now, I'm going to first show by plugging the numbers in, but then I'm going to show you that there is another way, a little bit of a shortcut, I guess, to finding the remaining 2 once you know one of them, okay, assuming that the degree of the equation is 3. Okay, so let me show you here. First, I'm going to test negative 1. I'm going to see, does negative 1 work in the equation? Well, let's see, because I'm looking at my list here of potential rational zeros, and now I'm going to try them out. So negative 1 to the third plus 7 times negative 1 squared plus 4 times negative 1 minus 12. So we have negative 1 plus 7 minus 4 minus 12. And this gives us negative 10, which is not 0. We're looking for 0. If we got 0, that would mean it is a solution. So negative 1 is not a solution. Well, what about 1? I'm going to plug in 1. And when I plug in 1, I get 1 plus 7 plus 4 minus 12, which is 0. That's good. Okay, so I did find one solution. One solution to this equation is x equals 1. But I know there's got to be more than one solution. The degree is 3, so I'm thinking 3 solutions. Now, sometimes you don't have 3 unique solutions, but you just kind of have to test to find out. What I mean by that is let's say this does factor, and I do believe it factors. We'll see that because we're going to find 3 rational solutions that work. But if we would factor this and we'd see the same factor twice, then that would be 3 unique solutions. So we've got to take multiplicity into consideration. Anyway, let's keep going here. So maybe we'll try negative 2. Is negative 2 a solution? So we'll plug in negative 2. And we have negative 8 plus 28 minus 8 minus 12. And this one works. That's nice. Okay, we found another solution, negative 2. Okay, we'll test 2 now. Sorry, that's a positive 2. Kind of. All right, we'll test positive 2 now. Okay, so 2 to the third plus 7 times 2 squared plus 4 times 2 minus 12. And if you can tell, like you might be able to tell right away that this isn't going to work. 2 to the third plus 7 times 2 squared plus 4 times 2, that's a pretty big number. And I'm only subtracting 12. So if at any point you can tell the answer is no, then you don't have to show all this work. Go ahead and show all this. All right, so let's see. This would end up being 32, which obviously does not work. So as you can see, this is quite time consuming. I'll go ahead and tell you that the other solution is -6. So let me show you why -6 works. We get -216 plus 7 times 36, 252, minus 24 minus 12, and that ends up being 0. So that works as well. So -6 is our third solution. But let's talk about another way we might do this, where we don't plug in every possibility to come up with our 3 solutions. So another way to do it is once you find one of them. Okay, so the very first one I found that worked was the number 1. Okay, so once you find one of them, you can use synthetic division. Okay, so I'm going to so I found that 1 worked. I'm going to put 1 in the box. Now, synthetic division is covered on another video. So if you need some help on synthetic division, check out that video. I'm going to go through this pretty quickly. Then I'm going to put my coefficient of the polynomial up at the top here. Okay, and then I'm going to do synthetic division. And I get a 0 here in the remainder position. That's good. If you don't get a 0 in the remainder position, then that means that this is not actually a solution like you thought it was. Okay, so I found 1 was a solution. I should get a 0 in the remainder position. Here's my number term. Here's my coefficient of x. Here's my coefficient of x squared. Then if you take the remaining trinomial that you got and you factor it, you will come up with the other 2 solutions. So I found 1 was a solution, and now I'm going to see that -2 and -6 are also solutions by factoring this. Okay, so this factors into x plus 6 times the quantity x plus 2. Okay, and then if we want to solve this equation equal to 0, then we get x equals -6 or -2. And notice those were the other 2 solutions. So you might find this as a shortcut. Once you find 1 solution, you can use synthetic division, come up with the remaining trinomial or whatever it may be, and factor and solve. Or maybe it doesn't factor. We're going to see in the next one. We're going to use this process here, and we're going to have to use the quadratic formula to come up with the other 2 solutions. Okay, last one in the video here. So I am going to start and list the potential rational zeros by first looking at the factors of positive 6. Not that that's going to change anything. Factors of 6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And then I'm going to look at the factors of 1, plus or minus 1. And when we put the factors of 6 over the factors of 1, since the factors of 1 are just 1 and -1, really this is our list of potential rational zeros. Okay, so here's my list of, these are the potential rational zeros. Now we do need to find one that works. before we're able to do synthetic division. Now you could use synthetic division to find one that works, but I think I'm just going to plug it in and then use my synthetic division. Okay, so I'm going to try -1. Does -1 work? -1 to the third minus 11 times -1 plus 6 is -1 plus 11 plus 6. And this is 16. Doesn't work. I'm looking for 0. Does 1 work? Nope. 1 minus 11 plus 6 is -4. Doesn't work. Okay, let me just jump to what I know works. The number 3. Okay, so this is why this process can take a long time to find that first rational 0, if it exists. Okay, so 27 minus 33 plus 6 is equal to 0. Got it. Okay, I found one, the number 3. I'm going to use synthetic division now to come up with the other factor that's going to end up being a trinomial. Okay, notice I put a 0 in because if you look at the equation, there is no x squared term. So if I'm going to use synthetic division, I do need a 0. And I'm going to use synthetic division, so drop down the 1, 3, 9, -2, -6. I got a 0 in the remainder position. That's good. You need that. If you don't get a 0, something went wrong. Here's my number term. Here's my coefficient of x. Here's my coefficient of x squared. So I need to now solve x squared plus 3x minus 2 equals 0 to come up with the other 2 solutions to this equation. Now this time, this equation does not factor. What that tells me is if I had continued to check the potential rational zeros, I wouldn't find another 2 that work. It looks like our only rational 0 is 3. This does not factor. So my other 2 zeros or solutions, they must either be complex or irrational. So let's see what happens here. So here's the quadratic formula. I'm going to use it to help me come up with the other 2 zeros. And so we have -3 plus or minus the square root of 9 minus 4 times 1 times -2. The whole thing is over 2 times 1. This would be -3 plus or minus the square root of 9 plus 8, which is 17, over 2. Okay, so my other 2 solutions are irrational. So like I said, I wouldn't have had any luck had I continued to check the potential rational ones. I would only found just the number 3 that works. But there are 3 solutions. Where did I write? I guess I never started writing down my solutions. Okay, so one solution is the number 1. Sorry, the number 3. I apologize. Number 3, thinking of the other one. The number 3, as well as -3 minus square root 17 over 2, as well as -3 plus square root 17 over 2. Well, that was fun. Okay, so had to use the quadratic formula there. The trinomial that we were left with did not factor, so that's what made it necessary to use the quadratic formula. Well, I hope you found this video helpful, and I hope you have a better understanding of finding rational zeros in polynomial functions.